who's going to talk about an approach to generating text-based IDEs with syntax completion from syntax specification.
I'm Isao Sasano from Shibara Institute of Technology, Japan. The topic is about syntax completion, which is usually implemented on various kinds of IDEs like Eclipse or that kind. And developers of IDEs have their own policy to cope with incomplete program text because syntax completion is usually used for the currently being input program text, so which is incomplete, and may not specify or explicitly describe the functionalities. And proficient programmers may like to know the functionalities precisely. And several decades ago, structured editors, or maybe called projectional editors, like synthesizer generator or mentor, have been developed. In this kind of structured editors, behaviors of functionalities are formally specified. So this is a good point. And of course, syntax completion is easier to implement. But structured editors prevent programmers from freely editing text usually. There is only one exception, which is pointed out by the reviewer of this conference. The exception is the editors produced by the LRC system, which is also several decades ago developed. I mentioned this one in the related work. So the objective of this work is to develop text-based editors that provide formally specified functionalities, especially syntax completion in this work. So syntax completion is formally specified. This is one point. And syntax completion is implemented by reusing the code in parsers as much as possible. And behaviors of syntax completion can be predicted by programmers if they hope, having some knowledge of error parsing. This is a very simple example. This is a subset of a standard ML language. And suppose here is the cursor, and then if we push the tab key, then this kind of candidates is popped up. Or this may be another typical case. There is 1, 2, 3 open parentheses, and then here is the cursor, and then push the tab key. Then this kind of candidates are popped up. So in this case, 3 close parentheses, or 2, or 1 close parentheses, or some identifiers. So what we'd like to do is to formally specify the remaining part of the program text after the cursor position by using error parsing in this work. Error parsing may be a little bit old technique, but we've considered this as a good starting point. And then in the remaining part, we use the terminology in the original paper by Donald Knuth about the error parsing. Then firstly, we'd like to introduce one notion about postfix sentential forms, which is based on a sentential form, which is introduced by Donald Knuth. A sentential form is a sequence of symbols that can be derived from the start symbol. This is the sentential form. And then, suppose here is a cursor, and then alpha is some sequence of symbols. Then we'd like to specify some remaining part which is not being input. I will highlight that one as dead. in this case, alpha and beta together form sentential form. Then this is the definition. So alpha is the sequence of symbols. And when alpha beta is a sentential form, then we refer to this sequence beta as a postfix sentential form with respect to the sequence alpha. But there are infinitely many postfix sentential forms for alpha in general. Then the candidates that are expected by the programmers are those which corresponds to or close some of the syntactic components like close parentheses or that kind in the typical cases. So the our idea is this one. This notion can be maybe captured by using the concept of reduction in error parsing. So the candidate to be completed is this one we consider in this work. Alpha be the sequence of symbols, which is the result of partially parsing the code up to the cursor position. And then a sequence of symbols gamma, which is not being imped yet, is a candidate to be completed when a postfix of alpha, some postfix of alpha gamma can be reduced by some productions in the target grammar of the language in error parsing. But there are still infinitely many candidates in general. Then we'd like to choose some suitable final subset from the candidates specified in the previous slide. We show this by using examples in standard ML instead of giving formal specification this time. Then this is a very small subset of standard ML, identify and abstraction and function application and parent sized expression and let expression. Then let's consider this example. Let var add equals fnx arrow. So this part is a partially input function abstraction. Then here is the cursor position. Then at this point, the symbols on the stack in the error parser becomes like this way. I omit the states, just the symbols. Then add becomes ID and x becomes ID. So the stack is this one. Then the one candidate is ID because by inputting ID, then ID can be reduced by this production, m is equal to ID. And the second candidate may be m because if we add m at cursor position, then this red part, fnid arrow m, can be reduced by this production. And the third candidate may be this one, m in m end. This is a candidate. They, by adding this one, then we obtain this kind of things in the stack in the error parser. Then this can be reduced by this production. So the whole part is the target of the reduction in this case. Then there may be considered many approaches, and I present two approaches here. One is to use the internal information of the error parser. Another is to transform the given syntax definition to one for the program text up to the cursor position. Then this time we adopt the second method. Then in the second method, starting with the definition for the language, we transform this one to obtain syntax for the prefixes up to the cursor position. Then we get this kind of syntax. And I present the algorithm in the paper, but I omit the explanation. So this is the syntax for the prefix. Then I implemented this one. So currently, I've manually written the code for computing candidates from the syntax tree for the partial code up to the cursor position. Then I implemented for the tiny subset of standard ML, and I used an Emacs mode. And I implemented in Emacs response C language. The C program, which is handwritten by me, calculates candidates from parts trees up to the cursor position. And then when the tab key is typed at the cursor position, then Emacs and C program communicate via TCP/IP like this way. So Emacs sends the whole the program text up to the cursor position and the location of the cursor, and then return the candidates to be popped up to the Emacs. There are several related work. One is this one, SLE 2016. They represent incomplete program text using placeholders. And in their work, incomplete program text is syntactically complete except for the placeholders. So this is a difference with our work. And when users select a placeholder, then syntactic candidates are popped up, which suits the place of the placeholder. And in contrast, we do not use placeholders or that kind, and allow arbitrary program text after the cursor position. So that is, we ignore everything after the cursor position. Another major related work is by Kuiper and Joao Saraiva in compiler construction in 1998. They developed a system called LRC, which is unfortunately no longer available now. I communicated with Joao Saraiva before. This system generates graphical language-oriented tools in general. And it takes a high-order attribute grammar and generates attribute evaluators. And as an instance, the system can generate editors. And users can edit the code via GUI or CUI on the editors generated by LRC system. But editors with a syntax completion functionality have not yet been generated by LRC. There are much work to be done. One future work is this one. This time, I have manually written, but mechanically derived the syntax, partial syntax from the complete syntax. And this might be related to some grammar transformation. And we'd like to give an algorithm for generating code for syntax completion and argue some properties of candidates to be completed. And another future work may be this one. Give a formal specification of candidates by using the internal of error parsers. And recently, Kwan-Fu Choi in KCC 2019 developed libraries for writing error parsers using a single language. Writing parsers can be done just by a single language, not by using a .y file in error parsers or that kind. So it is similar to a PLY system in the Python language or that kind. where the important point is the users can access the internals of error parsers by their system. Then I am planning to implement syntax completion by accessing the internals of error parsers by their tool. Then I show one demo. Oh. So I have implemented Emacs mode, which communicate with the C program. So this is a partial program up to the cursor position in standard ML language. Then I push tab key here. Then there are 1, 2, 3, 4, 5 candidates popped up. Then I can select one of them like this way. Then let's select the second one. Then it is completed. And 3 dots. This one corresponds to the M construct in the language syntax. Okay, that's all. Thank you.
Questions? Yes.
Hey, it looks like the 3 dots actually are a placeholder.
You mean these 3 dots?
Yes, that's like a placeholder, right?
It seems a placeholder, but this is a part of the candidates popped up. So in their work, the placeholders exist before the showing the candidates. This is part of the candidates, which should be later rewritten by the programmers. This is our intention.
Another question? No.
The partial grammars look very much like the Brzezowski derivative. The
Very much
Brzezowski
like.
derivative of grammars from 1962.
Derivative.
Yes.
Derivative.
Yes. It's been generalized to context-free grammars.
Derivative.
Yes.
I have never heard of derivative. Anyway, derivative.
So another question I had is, you've shown that there's different variants of continuing with this work. So I wonder what would you recommend? How should we compare different completion systems? How do we compare them?
Compare the
Yes.
completion systems. Do you mean the future work 1 and 2?
No,
Or
how can we compare them in general?
in general?
One approach is better than another.
So maybe we can compare by the properties of the candidates to be popped up. It is one.
So in the SLE paper that you cited, there was this completeness property, right? There was an actual property about that you can actually, just using code completion, can arrive at any program that the grammar allows. Right? So I'm not sure that's a useful property for the programmer, but it's at least it's a property. Do you think that's a good idea to look more into properties, or should we do user studies, or what should we do? User study.
So finally, we should provide functionalities which programmers expect. But so for the first point, we may be able to argue the formal properties firstly.
Okay, so let's thank the speaker again.